time to start. We would like to, the first speech will be from Andrit Kulai. He's Professor of Horticulture at the Agricultural University of Tirana, Albania. And he will talk about a novel screening method in breeding apples for optimal stomatal behavior. The floor is yours.
Good morning. It's a pleasure to be part of this very important symposium and to present the research that we have conducted in the last years. So despite the title of the presentation, I would like to explain at the very beginning that even if we talk about screening, we're not referring in this case very much to molecular markers, which are currently used and we have discussed during these days, but rather physiological markers. And in the case of talking about breeding program for apples, is rather a proposal to open a breeding program on a physiological breeding program. And then regarding the stomata behavior, this is not like the other traits that we generally try to work on breeding, but it's a complex mechanism and therefore there's many genes involved. We're talking about this because currently the water use efficiency is a great challenge, especially now with the global warming and the reduction of the availability of water. So in such a changing environment, optimal behavior for stomata could be an important trait in physiological breeding. And again, this is a proposal, and this is the best audience to propose such an idea of working on optimal behavior for stomata. So, for example, stomata behavior only in response to severe stresses could be better than stomata that maintain a kind of low conductance continuously. Or, for example, if in some cases the strategy would be that the restriction of the stomatal opening only during the period of the day where the evaporative demand is low, in the morning and evening hours, could improve the efficiency and also the draw tolerance. So, as we can see, there are basically two distinct but related trade-offs, either between the maximum relative growth rate and the draw tolerance, and also the maximum relative growth rate and the plant water use. So the idea type, a term which is commonly used by the breeders, would be for any environments involved in this kind of compromise between the water conservation and the productivity mechanism. And the optimum balance will depend how arid or how much arid is the environment. So this will depend mainly on stomata behavior. But as the title of this presentation is how to screen genotypes for stomata behavior. So this is the first issue that we have to face before we embark into a potential breeding program. So the current practice for measuring stomata conductance is by using porometers. But actually, we're working with fruit trees, with complex canopy, very heterogeneous measurements because of the different exposures of leaves to radiation, temperature, and water pressure deficit. So when we try to compare the canopy conductance at the tree level, and we want to distinguish between different genotypes, then it becomes very, very complex. So what we need in the very beginning is a fast and reliable method to measure, to screen for stomata behavior and transpiration. So modeling is an approach to overcome such difficulty, and that's what we try to solve in our research, to develop a simplifying modeling approach to screen fruit tree genotypes. Here I present research on apples, but the model can be used for any fruit tree. So for the canopy conductance behavior. By simplified modeling, I mean that it uses the minimum variables which are available by any meteorological station. So the work presented is based on the research that we have conducted in the last years on commercial cultivars grown in the very warm, semi-arid region of Albania, where apples are cultivated because of to use the earliness and also the closeness to the main cities, to the main markets of apples. Because in Albania, the proper area for cultivation of apple, and where apple is found mostly, is the eastern part of territory. So we've been working with these commercial cultivars found there, and we present this because we have sufficient data for the validation of the model. But anyway, we tried also to use also another location, which is a more temperate climate in Kosovo, in order to find out if the model will also predict the stomata behavior and conductance in a climate which is more variable than the one which is located in this dry Mediterranean area. So this is a summary table of the experiments, the cultivars that we use, the rootstock, the climate differences, and mainly the leaf area index was almost very, very close to each other, because that is very important when you try to compare for canopy conduction and transpiration. So how did we came up with the calculation of the transpiration? We used the sap flow sensors based on steam heat balance method, and we installed that in the main leader of the trees for each genotype. So as I said, we need some meteorological variables which we got from the meteor station, and from that we're using a software design, Mini32 software by EMS in Brno, Czech Republic, by our colleague Jiří Kučera. We calculated the vapor pressure deficit, which is basically driving the transpiration of the trees and also the potentially evapotranspiration. So since we wanted to, at a certain point, we wanted to apply some water stress, we also measured the soil water potential, and we produce a water deficit peak at a certain point. So the modeling part, modeling procedure takes into consideration that differently from the short grass, the canopy of the trees is very tightly coupled to the atmosphere because of the large roughness, and in fruit trees the transpiration will mainly be modulated by the canopy conductance and leaf to vapor pressure deficit rather than from solar radiation, which is the case of the short crops. So just short theory reminders for the breeders in the audience. This is the Pemman equation, which describes the evaporation of the water from the homogeneous short tree norm, but which is, as I said, is quite different from the canopy of the trees. So we modify the wind part of the Pemman equation, which replace it with the turbulent diffusion theory-based expression, when the wind speed dependent aerodynamic conductance is calculated from canopy parameters. So what general approach applied is that since the stomatal conductivity depends on the radiation and VPD, the parameterization process is usually based on daily means. And then the common approach is to rearrange the equation that I showed before for stomatal conductance, and then find the best fit with the radiation and VPD. But in our approach, instead of using the daily means, we use the diurnal courses of the variable, and we use a different formula to describe this influence of stomata closure to VPD, and then the parameterization process performs direct nonlinear multiple regression analysis of any equation. So that brings more detail to the analysis, and it helps us understand the canopy water use established from the point of view of daily dynamic. So this is the common equation which is used, the Lohammer equation. You see in the upper graph, you see the stomata opening with the increase of irritants, and the stomata closer with the increase of VPD. So in cases of stress, when the air is very dry in the air, the stomata are closed. But obviously, when the stomata closes, the photosynthesis stops, and then there is no growth. So this is the common equation which is used by Lohammer. In our case, since we found that there was a missing degree of freedom in the VPD part of the Lohammer equation, we wrote a more complex formula, but which gives more flexibility to stomata behavior, and we see that there is a different curve here. It doesn't, it mimics the stomata closes so sharply under the low vapor pressure deficit. So basically, we wrote a complex PM equation, which already includes now the canopy conductance at the tree level, and we calculated the parameters which are used for the non-linear multiplication analysis. So we apply this without going into too much detail. So this is the model that we are using. And these are the variables that are needed and can be easily collected from meteor stations. The script used for the calculations, this is the parameterization window in the software. So here is, I only use very few of the graphs from the experiments just to show you. So this is the basic climate of the very warm semi-arid area. You see quite a high radiation values, very few cloudy days, and quite high temperature during the June-July season. So these are that kind of temperature will lead to a very high vapor pressure deficit values, and therefore to high transpiration. So this is a summary table of the experiments conducted, the values of the VPD and potential vapor transpiration. So this is the actual transpiration values of different cultivars or genotypes, if we call in this case. So we can, this is only a few days measurements to see the difference between cultivars. So how do they compare to each other in terms of transpiration? And here we have shown here the plotted over the calculated actual values, which is the red one, and the calculated one, which is the blue one, our model basically. And we see that this is to show us a visual test of goodness of fit. And we see that if we use the root mean square error to compare between the actual transpiration and calculated transpiration values, we find that the equation matches well with the seasonal pattern, and there are not very much periods of over or underestimation. So it suggests that the climates where these experiments took place, the model accounts for the seasonal variability of transpiration, with some few exceptions in case of cloudy days, occasional cloudy days, or in general transitory lower productive demand. So this is basically what we can use to screen genotypes for their canopy stomata behavior or canopy conductance. So here you notice this is the stomata conductance, or canopy conductance in this case, and this is VPD. So we see that when the vapor pressure deficit increases at a certain level, the stomata start to close. And we can get this data online from the field, and for a series of genotypes. And that can be used, we think, or we propose, that can be used as a way to screen genotypes. And here is a nice comparison of the stomata behavior of different cultivars as a response to increased VPD. So we have cultivars like Gala in this case, which closes the stomata sharply after exposure to high VPD. And we have other cultivars which has more gradual closure of the stomata. So we propose, we think that this is a way how to screen genotypes in a short time with a 10-minute resolution for stomata behavior. And then we can distinguish between cultivars and different behaviors of stomata. So the sensitivity of the model offers the ability to study stomata behavior to environmental variables. It can also be used for application of different agricultural practices. And the question is now, could it be used as a tool for quick evaluation of water stress tolerance in every genotypes? However, if in fruit trees in general, and apple in this case, we have a tricky situation because we have a combined tree. We have a scion, and we refer to stomata conductance in the leaf level, but we have also a rootstock, which is where in the root system we have the production of abscisic acid, which gives the signal to stomata closure. So we have also the situation where we have maybe to study for are we comparing between different rootstocks and how they react, or are we it's a combination between rootstock and scion where the leaves are. So it could be used for assessing genotype environmental interaction in relation to stomata response to abiotic factors, and maybe, as the title suggests of this presentation, maybe as a proxy physiological marker in selection for resistance. And that we can add to that also the measurement of the conductance to carbon dioxide for the photosynthesis. And again, we can start to maybe open a window or programs on physiological breeding for optimal stomata behavior. Thank you.
Thank you, Andret, for your nice presentation. Are there any questions? François? No? Yeah, François will upload this presentation while we are doing questions. So perhaps you can go a little bit to the side. Can anyone help François with uploading? Or do you know yourself? Yes, in Chinese. Okay. No questions? Well,
have you applied these methods to any other cultivars or potentially wild relatives?
Yes, we have also tested some local genotypes of apple. We have published this information in another study, in another paper. We tested the local genotypes of apples found in Albania, and we found similar differences both in stomata opening. I only showed the reaction to stomata closure from VPD, but it can also be used, the model provides also the stomata opening to radiation, so we can also compare cultivars between their saturation levels for the stomata opening.
How much time do I still have? Okay, let's go. Okay. Then I have a question. You showed that there are large differences in the amplitude between the size of the opening or the conductance, and in one part of today and the other part of today. But these are all under commercial growing conditions. That probably means that there is water supply when needed. So have you any idea how those cultivars perform with the stomata opening and closure and the stress conditions, and to which extent your program, your parameterization will also well describe those conditions?
Thank you. For the modeling procedure, we didn't apply stress, but when for the identifying the changes in stomata behavior to increase VPD, the values which I showed were during the stress period that we applied with 3 megapascal. So the lines that you were showing, the curves that I was showing before, were during the stress period.
Okay. Well, being a chap, I was not able to make pictures.